See, alkenes specifically have three type of reactions we'll go through. First, addition reactions. Next is substitution reactions. The third one is elimination. Addition means what? If you have a double bond, you are converting that into a single bond by adding two components to it. Or if you have a triple bond, first you are converting into a double bond, then you are converting into a single bond. That is addition kind. Okay. Substitution means whether you might have an alkene, on the alkene position somewhere you are removing one group and adding one. So that is substitution. Okay. Elimination means you already have a double bond, you are converting that into a triple bond. Or you have an alkyl halide here, something like that, H and X, you are converting that into a double bond. This kind are called elimination. Okay. So addition again is of two kinds, electrophilic, nucleophilic. Electrophilic word is used when you are adding the electrophile E plus. E plus means something like H plus, CH3 plus, X plus, like this. If you're adding an electrophile where that step is the rate determining step. Similarly, if you're adding a nucleophile and that step is the rate determining step, then that particular type is called as nucleophilic addition. Likewise, electrophilic substitution is also the same. If you are adding an electrophile, and I mean, if you're substituting or replacing some group with an electrophile, and that is the rate determining step, then it is electrophilic substitution. Like nucleophilic substitution is the rate determining step, then that will be the case of substitution type. Elimination kind, you can see E1, E2, EI, E1, CB. These are the type of elimination which you will notice. Got it? So we'll go one by one now. First, let us understand very simple concept of uh, terms like what is reactant, product, transition state, intermediate, activation, or activating energy, or activating complex. These are major terms that you need to derive from chemical kinetics. Okay, so let's see what are those terms. First, start with reactant here. Okay, if you have an reactant energy here, okay, and if the product energy is more than the reactant energy, if the product energy is more than the reactant energy, it is called endothermic reaction. And the energy difference between product and reactant is called as delta H of the reaction, and that will be greater than zero if it is endothermic. Got it? Secondly, the energy that is required for reactant to reach all the way to this highest energy state is called as activation energy, EA. EA is called as activation energy. See, what would usually happen is, suppose if I want a reactant to convert into a product. Now, reactant has multiple bonds in it. Okay. You are trying to break those bonds and make something new. That is what chemical reaction means, the same thing, right? You're basically changing the identity of molecule by breaking and making some new bonds. So while doing that from a reactant as you go towards product, while breaking them, you will increase its potential energy, because while breaking means you're trying to isolate the atoms, and atoms which are isolated are highly unstable. So which means that they will have very high amount of energy. That state where the bonds are either completely breaking or they are getting made, that particular location where it reaches to the highest energy possible is called as transition state. TS means transition state. Where the reactant reaches the highest energy state is called transition state. Now, what exactly the Hammond's principle suggests? According to Hammond's principle, the transition state will always have more structural features and stability analysis based on its nearest neighbor, based on its nearest neighbor, whoever is the nearest neighbor to it. Okay, what does this mean? Let me tell you. Suppose if I have an endothermic reaction, okay, best example, let me take one best example here, something like PCl5, as it's when you heat it, it will become PCl3 plus Cl2. Let's say this is one endothermic reaction on heating. Got it? Now, what happens from this reactant to go towards product? You require heat, and delta H of greater than delta H is greater than zero means that means you're supplying heat to the system. Okay, on supplying, first it reaches to this transition state, that PCl5 will start breaking into two new molecules, which is PCl3 and Cl2. So it reaches to the highest energy state here. Okay. Now what I'm saying, when it reaches to the highest energy state here, got it? This particular phase of that molecule will have more similarities with product than reactant. That means its stability, its structural features, correct? All of that would depend on how its product energy is, or how the product is, structurally how the product is. Got it? So these are the features that transition state will carry, and this is what Hammond's principle suggests. Everybody, I hope you understood this logic. Let me show you second one. Suppose from reactant as you go towards product, and if at all I take delta H here, this time delta H is negative because product energy is less, reactant energy is more. You call this as an exothermic reaction. Okay. And now this is the activation energy, and this is the transition state. Something like a reaction, N2 plus 3H2 giving 2NH3, let's say. This is basically an exothermic reaction. So energy is released in this case. So now the transition state which is being made by nitrogen and hydrogen together. Now that transition state where nitrogen-nitrogen bond is breaking, hydrogen-hydrogen bond is breaking, nitrogen-hydrogen bond is making, correct? That particular scenario of the molecules, it will have more features of a reactant rather than product. Why? Because this is the nearest neighbor. It would have more stability analysis. That means the stability of that intermediate depends upon the stability of the reactant. If the reactants are more stable, then the transition state will be more stable. Now tell me, if the transition state is more stable, this height will come down. Okay, because here it is high energy, that means less stable. If this energy is less, that means it is more stable. And secondly, if the transition state energy comes down, the activation energy also comes down. So less is the activation energy required. That means the reaction will go faster. Remember, the rate of reaction means the speed with which the reaction is proceeding. Now, the speed mainly depends upon activation energy's value. Higher the activation energy value, slower the reaction will go. Lower or smaller the activation energy value, faster the reaction will go. Okay, everybody clear on these 2 points? So in the first case, where endothermic reaction is operating, transition state will have all the features stability depending upon the product. If product is becoming more stable, so does the transition state, and transition state is more stable, that means the activation energy is lesser. And here it goes vice versa. If it is exothermic reaction, and transition state will have more features of the reactant, if the reactant energy is less, that means it is more stable, then the transition state's energy will also be less. activation energy will be less and reaction will go faster. Now, there is a third type of reactions. Now, listen up. In these reactions, I saw that a reactant is going towards product directly via transition state. That's it. So, these type of reactions where I write a single curve like this, these are called elementary reactions. This is elementary, this is elementary. Elementary reactions are one step reactions. They happen to go only in one step. There are no intermediates forming. Students, if you may recall, we learned certain intermediates, carbocation, carbanion, radicals, है ना, benzene, all of these. If these are forming during the reaction, that means those reactions are called complex reactions. If nothing of that sort is forming, a reactant is directly becoming a product. That means these are elementary reactions. Typically, if you have reactions like acid-base reaction, NaCl reacting with HCl, you'll get, sorry, NaOH reacting with HCl, you'll get NaCl and water. These are very fast reactions and they do not account for any intermediates at the during the reaction. So they go through some transition state, but immediately they'll give only product. So there are certain reactions where they happen to go either fast or even if they go slow, they might happen only in one step. But there are complex reactions, especially in organic reactions. You will see a lot of complex reactions where a reactant is first going through an intermediate. Intermediate could be a carbocation, carbanion, radical, any of those formation. And from that intermediate, then it is going towards a product. Then we say there are two steps happening. From the reactant, it is going to intermediate via one transition state. And from intermediate, it is going towards product via another transition state. So there are two steps happening. Okay. Both transition state 1, 2 are close to the intermediate, isn't it? Can you notice? This one and this one has much more closeness towards intermediate. So the features of the transition state, the stability of the transition state, the overall energy of the transition state depends everything on intermediates. And now I hope you understood why we learned so much of GOC. Because intermediate stability, intermediates structure, how does it look like, its features, they all define how the transition state looks like. Okay. And you might wonder why is the transition state is so important. See, transition state is a way to explain how the electrons are moving from reactant towards product. Got it? The movement of electrons while the bond is breaking, while the bond is making, this is called reaction mechanism. Got it? So the reaction mechanism depends upon how the transition states are being made, what type of transition states are made, what is their stability. Got it? How does the feature of the transition state look like? What is its geometry? What is its shape? All these analysis becomes essential to understand the mechanism of a reaction. I guess this part is clear, everybody. So, what have you noticed? According to Hammond's principle, especially if you have an intermediate, then the nearest transition states, right? I mean, the transition state which are nearer, they will replicate the features of the intermediate. Got it? This is what is Hammond's principle is all about. Next. Now, if you notice, whenever we talk about chemical, I mean, reaction mechanism, where we say that certain reactants are moving from reactant to product there, then there are three main features that you need to check. One is called nucleophiles, leaving groups, and bases. Nucleophile, leaving groups, and bases. Clear? Now, what does they do? What is the exact role of it? Let's see that. First, let us figure out what is the major difference between nucleophile and a base. When do you use the word nucleophile? When do we use the word base? See, nucleophile is a word or terminology used when we say that nucleophile is a terminology used when we say that, okay, it is electron, sorry, nucleus, nucleus loving species, nucleus loving species, which attacks on carbon positive charge or carbon delta positive charge, okay, but not on, not on H plus or delta H plus. In simple terms, if the species like nucleophile, I mean the species like something which carries negative charge, if its objective is to go and attack carbon which might be slightly delta positive or completely delta positive, then we refer it as nucleophile. But if it is attacking, if it is attacking H plus or delta H plus minus, delta H plus here, in that case, we call it as a base. So the base wise, as a base, this is clear. What do we call it here? See, it is proton loving species. Proton loving species which attacks on either H plus or H delta plus, but not on carbon plus or carbon delta plus. Then you call it as a base. Okay. This is the simple difference between nucleophile and a base. Let me show you with an example. Suppose I have something like CH3, CHH, CH2, and Cl. Now notice, because chlorine has more electronegativity, it will impart delta positive charge on carbon. That imparts delta positive charge on this carbon. Now what happens? If something like CH3O minus is attacking, it will think in two ways, everybody. CH3O minus thinks ki carbon has positive charge. Here carbon has slightly positive charge. Why won't I go and attack here? So it will choose this direction first. Okay, this is one direction where it can attack and try to relieve the chlorine out of it. Got it? Then there is another approach. The other approach is, instead of attacking carbon directly, why can't it go? Why can't it go and attack this hydrogen? What would happen? In that case, carbon here, if it takes away H plus, this carbon will get negative charge. That negative charge can be pushed to remove the chlorine. So chlorine is not being removed directly, it is released indirectly. Now have you noticed it is the same CH3O minus. This is no different. This is the same CH3O minus. But its role is different in both cases. In first case, it is acting like a nucleophile. Here it is a nucleophile. While here it is acting like a base. Here it is acting like a base. But have you noticed something in common in both of them? Everybody. What are they doing? They are going and attacking the space where either carbon is present or hydrogen is present to ensure that chlorine is relieved. correct? And is chlorine coming? I mean, what does chlorine do here? Chlorine will take the bonded electrons and leave the molecule. That's why that's what this arrow suggests. When I put the arrow towards chlorine means that entire bonded electrons are being shifted towards chlorine and then chlorine is leaving. So once the chlorine comes out, it would have that extra electron. So it is coming as Cl minus. So it will come as Cl minus. Clear everybody? That species which will leave the carbon and comes out with the bonded electrons is called as leaving group. That's what we call it as leaving group. So any species which leaves the carbon and comes out with a lone pair is called as the leaving group. I guess this basic understanding is clear, everybody. What is leaving group means? Right. Now, there are many type of leaving groups. Now notice this one. Suppose if I ask you the acidic character of molecules, like for example, Hi, HBr, HCl, HF. We know that down the group for hydrates, the acidic character increases. So Hi is the strongest acid. And we also learned from ionic equilibrium that after losing H plus, the species left is called as conjugate base. And the conjugate base is I minus, Br minus, Cl minus, and F minus. So in this, which one is the strongest base? F minus. F minus being the strongest base here. Correct? You know that weaker the acid, its conjugate base will be stronger. So I'll just write down here, this is weak acid, which makes it strong base. And vice versa. This is strong acid, which makes it weak base. Okay. Now, what has been noticed during the leaving group is like this. Suppose if you have R, OH, correct? If suppose a chlorine is being trying to push it away, a chlorine is attacking like a nucleophile, I would say. In that case, what do I expect? I will expect that this Cl minus will go attack the carbon, push this OH minus out, and thus make it into RCl and OH minus. RCl and OH minus. Now, again, I'll keep coming back and forth here. Please be with me on this one. Suppose if I compare the acidic strength of water and HCl, everybody, which one is more acidic? Obviously, HCl. HCl is a very, very strong acid. So, after removing H plus, what would be the ions which will be left? You'll be having OH minus and Cl minus. And you know that if it comes to the basic character, because water is extremely weak acid, that makes it OH minus as a powerful base. So OH minus is a strong base as well. Now, when you are trying to analyze a nucleophile versus a leaving group, have you noticed this is a nucleophile and OH minus is a leaving group because it is coming out with a pair of electrons. That's what the definition suggests. Now you need to check which one is more basic. OH minus is more basic. Now, in a chemical reaction, everybody, a reaction is more spontaneously feasible in the direction where a strong species is giving a weaker species, but not the other way around. That means you cannot expect a stronger base to generate, sorry, you cannot expect a weaker base to generate a stronger base or a weaker acid to generate a stronger acid. But the other way around is correct. That is, a stronger acid can generate a weaker acid, and stronger base can generate a weaker base. Which means, is this reaction chemically feasible? Answer is no. Why? The basic character of OH minus is more than Cl minus. Hence, this reaction will be more favorable in the backward direction and not in the forward direction. Correct? Now, through the mechanisms, you will learn this logic that you will try to make these groups slowly when OH minus is not a very good leaving group. You are not able to relieve it out of carbon and push chlorine to attack. Then what you will do here is this. First, an alcohol is been added to some kind of an acid. Okay. Then alcohol as a base, it will accept the H plus and becomes ROH2 plus. And once it becomes that, then you attack the chlorine as a nucleophile, expecting this time that it will push here to carbon, relieve water out of it. Then what are we expecting it to get? I'll get this as RCl plus H2O. Okay. And that makes this as the leaving group. Got it? So now what you're doing is you're comparing Cl minus and water again. This time, if you compare the basic nature, you know that Cl minus is still a stronger base than water. Water is an amphoteric group, which is an extremely weak acid as well as extremely weak base. Now, can you see chlorine is relatively stronger than water? So that means this reaction is feasible. That's how now this reaction works. Okay. So, what is the conclusion or what is the important note out of it? That is, okay, weaker the leaving group, sorry, weaker the base, better is the leaving group. The leaving group will be stronger in this case. Got it? Anybody has any doubt with nucleophile, base, and leaving group? Please talk to me right now. I'm pretty sure there is one thing you must have realized that basic character, nucleophile, and leaving group, these kind of species, they majorly depend upon their acidic strengths. Then only we can define their basic strength. Then only we can suggest whether it's a good leaving group, bad leaving group, whether it's a good base, good nucleophile, bad nucleophile, and so on. That's why it's highly recommended to learn certain pKa values. If you may recall, we have already done this in GOC 3, where I told you to remember certain pK values so that you can converse with bases and acids more easily. In this case, you can see alkanes, amines, ammonia, alcohol, water, phenol, very important cases. And this is a weakest of the acid, which makes it strongest of the base. Strongest of the base is the least stable one. So stability wise, this is the weakest. Stability wise, phenoxide is more and basic character is less. So that means because phenoxide relatively is a weak base, that means it is a good leaving group. So that's why you can see phenoxide is a better leaving group than OH minus, then RO minus, NH2 minus, RNH minus, RCH2 minus. Very conceptually, you should be able to figure out a reaction is feasible or not. Okay, let me show you how. Okay, for example, if at all I simply write it like this, suppose I wrote this as sorry, RNH2, RNH2, and I'm trying to react this with, you know, OH minus, correct? Then I have PHO minus, then I have, okay, CH3 minus, then I have RC triple bond C minus, Then I have Cl minus, okay, and then I also have Ro minus, correct, and then I have RCOO minus. These are all the nucleophiles I'm trying to attack it. I'm trying to attack it and remove NH2. If I do that, what I'm expecting, what is the expected reaction? Then we'll see whether it is feasible or not. The expected reaction is like this: ROH plus NH2 minus, ROPH plus NH2 minus, and RCH3 plus NH2 minus. Sorry, RC triple bond Cr plus NH2 minus, RCl plus NH2 minus, ROR plus NH2 minus, ROOCr plus NH2 minus. These are the reactions that you expect. Now, will it happen or no? What do you check? You will simply check out the leaving group nature. Have you noticed that any NH2 minus is a weaker leaving group than alkoxide, then hydroxide, phenoxide, and of course, if those are the ones, the others are even bad than that. That means RCO minus is even better leaving group than NH2 minus, then Cl minus, then Br minus, then SO3 minus, and so on. In that case, do you think because it is a stronger base, do you think OH minus can replace that? Answer is no. So that means first case no, second case no, third case yes, fourth case no, here no, no, and no. So only one reaction is feasible in this case. Everybody clear? This is how you notice the feasibility of the reaction, whether this will happen or not. Clear? Right. What if I do the same thing and this time I want you to recognize whether these reactions are feasible or not? Same thing, but only thing that I'm changing is phenol here. So one thing I'm changing here is phenol, PHOH, and the phenol reaction is the only one which I'm changing here. Here we will get this as, let's say, NH2. That means I'm replacing that with NH2 minus, and expected product is this. The expected product is PHO minus, PHO minus, PHO minus, PHO minus, PHO minus, PHO minus, PHO minus. Everyone, please check and let me know which is relevant, which would happen, which will not happen in these cases. You can go through the pK values, you can go through their basic character. Think about it. I'll give you a minute's time. I check first one. OH minus replacing PHO minus. Is it possible? Go and check. But PHO minus is a better leaving group. So first one is not possible. Second one is possible, definitely possible. NH2 minus is a weaker leaving group, correct? CH3 minus definitely possible. RC triple bond minus definitely possible. Cl minus impossible. RO minus definitely possible. Acid replacing it impossible. I mean forming an acid, sorry. Okay, forming this ester form. Is it possible? No, not at all. Clear? So I hope all of you understood this logic. Yeah. What happens to the leaving group? Okay. Whether the reactions are feasible or not. Right. So everybody, Jumping onto the mechanisms, let me keep reminding you what all things we are doing. First, we have learned the terminology of the kinetics. What is reactant, product, transition state, activation energy? What is RDS, rate determining step, which means the slowest step from which the reaction is happening. Okay, correct. These are basic fundamentals we learned. Second, we learned that there are three important terms during the mechanism. One is nucleophile, base, and leaving group. They all look alike. They are all same. You can say one species is a nucleophile, leaving group, or base, depending upon where exactly it is present. What is its role? And that particular reaction, what is its role? OH minus can be a good leaving group. It could be a good nucleophile. It could be a good base, depending upon the situation and the reaction. Okay. Now, slightly going ahead, we learn one more important term known as what is the types of solvents that we use for the reactions. Generally, there are two types of reactions in a broad spectrum which we observe. Okay. One broad spectrum which we observe is, you know, two types of solvents which we observe is polar and non-polar. Okay. You can see types of solvent. So there are two types of solvents majorly. One is non-polar type, non-polar, and the other one is polar. Within polar, we have two kinds now again, which is polar protic solvent, and the other one is polar aprotic solvent. In simple terms, if you have dipole moment being zero, resultant dipole moment being zero, then it is non-polar. If it is non-zero, it is polar. This is the first distinction. Second, if it is non-polar, sorry, if it is polar, and if it has polar protic, protic means a hydrogen which is sufficiently polarized. Okay, polar protic means a hydrogen which is sufficiently polarized. Like these cases, you can notice water, alcohol, acid, in all these cases, the hydrogen present on it is sufficiently polarized. That means it will have sufficient delta positive charge on it, like this. We can have sufficient delta positive charge on it. Okay. Next, polar aprotic. Polar aprotic means these are the solvents which have no polarized, hydrogen, but they are polar in nature. So, for example, hydrogen is present with carbon. Carbon does not have, does not give enough electronegative difference to polarize hydrogen. So, such kind of cases, ethers, you can see ethers, ketones, you know, amides which are substituted, DMSO, that means dimethyl sulfoxide, DMS, that means dimethyl sulfur. Okay, if this is hydrogen, this is called DMF, dimethyl fluoramide. Got it? Or formamide. Clear? These are all those solvents which do not have a polarized hydrogen on them. All good? So this is major type of solvents. So what are non-polar? Non-polar means whose polarity is completely, I mean the dipole moment is zero, like benzene, CS2, okay, CCl4, correct? And even if they are extremely low, we can categorize them into the same thing, like CH3. You can say there is slight polarity, but that is very, very low polarity. Even for that matter, we can have CCl, I mean CH3Cl, extremely low polarity. Polarities, I mean, overall polarity is not very high. Such cases can be categorized into non-polar types. Okay. I think the solvent type is also clear, everybody. Now, notice leaving group. I told you this already. When do we think whether it is possible or not? Okay. Now, it mainly depends upon the basic character, everybody. So, if Base wise, it's a stronger base, then it's a very, very weak leaving group. So you can see if you go from left to right in the periodic table, everyone, that is, if you go from CH4 towards NH3, then H2O, then HF. If you compare the acidic character, you know that HF left to right, the acidic character will increase, which makes what happens to the basic character, it should be reverse like this. So that's what it is. So you can see here CH3 minus is a stronger base than NH2, then OH minus, then F minus. This is the basic character. And basic character and leaving group ability will be same. Likewise, if you have water and H2S, you know that down the group acidic character will always increase. So if you see water and H2S, H2S is stronger acid. If this is stronger acid, then its base will be weaker. So hence, since water and H2S together, if you compare leaving group wise, down the group, molecule which is strongly bonded, oxygen will be strongly bonded, sulfur is weakly bonded. So I can say whichever is the stronger base that can leave more easily. Not just that, even if you have OH minus and HS minus also, HS minus is a weaker base, so it can leave more easily. Next, if you compare ammonia, water, and N2, see, left to right, ammonia will be very difficult to leave. Water is slightly better acidic, so it will be easy to leave. But when it comes to N2, right? Okay, N2 is a very, very good leaving group. Why is that very good leaving group? Let me show you. Suppose if you have something like an alkyl connected with N2 plus, and as soon as it becomes R plus and N2, have you noticed that nitrogen as it left, it has become a neutral and extremely stable species. Nitrogen gas is a very, very stable gas, stable inert gas, correct? It's hardly making any reactions as such, which means it's a very stable gas. So it will try to relieve out from alkyl group as soon as possible. It doesn't want to hold that positive charge and stay there. Okay, that's why nitrogen is an extremely good leaving group. N2, RO minus and RS minus, like I said, down the group, leaving group is better. And now if I compare these four, it comes from their respective acids. This is water, HX, OR, and RCO minus. So if I compare these four, let's say I'll put this as A, B, C, and D. Then you notice that, you know, uh, ROH, alcohol, is the weakest base, sorry, weakest acid, which makes it C as the weakest leaving group. And next, if it comes to water, it is the next weak acid, which makes it the next one, which is A. And thereafter, carboxylic acid. Carboxylic acid is weaker than HX, so that makes it D. And last comes B. That's why halogens are pretty good leaving groups, except for fluorine, of course. Fluorine is not a great leaving group, but yes, chlorine, bromine, iodine is a very, very good leaving group. And the best is iodine, because iodine's coming from HI, which is the strongest acid. HI is the strongest acid in organic compounds. I mean, when you compare all the organic compounds, HI is the strongest acid. So therefore, I minus is the best leaving group in this case. And likewise, if you compare alcohol, water, phenol, acid, and sulfuric acid, sulfuric acid is the strongest acid, which makes it as a best leaving group. So this is the best leaving group, then carboxylic acid, then phenol, then water, then RO minus. Likewise, these two are coming from CH3 COOH acetic acid, and this is coming from CF3 COH trifluoroacetic acid. You know that trifluoroacetic acid is very strongly acidic compared to normal acetic acid, so which makes it a better leaving group as well. CF3CO minus is a better leaving group. Okay. Likewise, you can see OTS. OTS means what, if you have a benzene with methyl group and then we have a sulfate group on it, this is basically a toluene with sulfuryl group, correct? Let me show you while writing. Okay, this is toluene plus sulfonyl group, correct? This we have cut short in organic to say this as TSO minus. This is TSO minus. TS is used for toluene sulfonyl group. So wherever you see TS, which means it is about toluene group, on para position, there is a sulfonyl group present on it. And if you have O minus, this is S double bond. Up to this is toluene. See, this much is toluene. Sorry, this much is TS. The short form of that is also called as tosyl. TOSYL means this much, tosyl. This is tosyl. With O minus, it will become tosylate or TSO minus. Got it? This is TSO minus. Benzene with SO3 minus does not have a short name for it. Okay, it is simply called as benzosulfonyl oxide or benzene sulfonate. Correct? But if you have Br, you call it as brosylate. If you have NO2, you call it as nosylate or nitrosylate or nosylate. Let me write down the other word. Nosylate. Got it? And you write it as ONS, this is as OBS, this is as OTS. And if you have CF3 on the other end, instead of benzene and NO2 and all, if you have CF3, this is a very strong leaving group. That makes it TF. Okay, this is called, trifluoro. You have a trifluorosulfonyl group, so short form is TF. And in generally, while conversing, we call it as triflate. OTF means triflate. Got it? So tosylate, brosylate, nosylate, triflate. If you compare the leaving group of these, triflate is definitely the strongest leaving group. Reason being, it is a very, very strong acid. Relative to all, that is the strongest acid. Then comes nosylate, ONS. Then comes brosylate, OBS. Then comes tosylate, OTS. But all four of them are excellent leaving groups. They can be easily replaced by other groups because by nature they are all sulfuric acids, and sulfuric acids have a very low pK value. That means their pK value is -5, -6, -10, and so on. Okay. So I guess all of you got a gist of it. What is leaving group and how they are connected? Yeah. Samyak, yes, Vacha.
Sir, can you go to the first one?
Sure. Please notice.
Uh, yes, sir. Can you repeat this? Like
Sorry,
how
I
did you
put the
get
order reverse way. Sorry, thank you.
Yes, sir.
Should have been the reverse way. Yeah. So because fluorine, HF is the strongest acid, F minus is the weakest. I was showing the acidic character, sorry, basic character. Now we are writing a living group character. Living group character means weakest base. F minus is weakest in this. Okay. Please do check others if all of you have got this point. If you are carrying your pre notes, please make sure you write the answers. Shall we go ahead? Now let's come to the mechanisms, everybody. We'll start first with even mechanism. Okay. E1, why it is being used, I'll explain you one by one in detail. Check it out. The best reference for, elimination reactions is to use alkyl halides as the reactants. Imagine if alkyl halides undergoes an even mechanism, then usually the solvent itself will act like a base. What does that mean? See, this is an alkyl halide. When you treat with a base like ETOH and heat, then ETOH as a base, as a base, will extract the proton from this position, remove the chlorine out, and convert that into a double bond. Okay, and the Cl minus which has left will again take the H plus from the ETOH which has taken the H plus earlier and converts it to HCl. Let me show you step by step. Now, when you have typically a polar protic solvent, like ethanol is a polar protic solvent, in that case, you can see CH3, CCH3, CH3 and chlorine. Now this, right, in the presence of a solvent, right, polar protic solvent, it will ionize into carbocation and radical easily. So it will become plus and Cl minus more easily. It will become plus and Cl minus very easily. Okay. And getting a carbocation is a rate determining step. That means it's the slowest step of the reaction. This is the slowest step of the reaction. And once you get a carbocation, it can undergo rearrangement also. Got it? But in this case, it is already on the most stable form. CH3, CH3 plus charge. I'll just write down here, can undergo rearrangement. Can undergo rearrangement. Can undergo rearrangement. After the rearrangement is done, now comes the role of the solvent. What does the solvent do here? Okay. Just a second, everybody. Notice. Once you get this carbocation here basically we have CH2H, and then I'm taking ethanol as a base. This base will extract proton from here. While extracting proton, this bond will shift onto this carbon, making this into CH3, CH3 with double bond CH2, and this will become ETOH2 plus. And this step, even if you do not write, that is totally fine. That is OCH2 plus the chlorine which has left will take away H plus, and again solvent will be back and HCl will be evolved, because that is the overall reaction which is happening. Got it? I guess the mechanism type is clear. Yeah. The solvent itself has to act like a base, because solvent ethanol is a very weak base, and that's the reason why heat is essential to make it happen. Now let me explain you why this heat is essential as well. See, generally whenever you make an elimination reaction, please check it out carefully. If at all I write this reaction again, okay, check this out. I started off with chlorine plus ethanol, correct? And that has become an alkene plus HCl plus ethanol, correct? Again, ethanol is coming out. So if I remove these two, ethanol and ethanol from here, so what is the overall reaction suggest? Overall reaction suggests that this is the overall reaction that has happened, correct? This is the overall reaction, guys. In the overall reaction, have you noticed something? In the overall reaction, I had one reactant converting into two products. One reactant going converting into two products, which means the delta S of this reaction is positive. That means its entropy is increasing. Second, while making these products, I am breaking one sigma bond between carbon chlorine. Sigma carbon chlorine bond is broken. Sigma carbon hydrogen bond is broken. While what am I making? I'm making a pi carbon carbon bond and one sigma H and Cl bond. This is what we are making. So left side is breaking, right side is making. But you know that breaking two sigma bonds is more challenging than making one sigma and one pi. One sigma bond and one pi. Which means energy is in a way required. That makes delta H of the reaction as positive. Delta H of the reaction is positive. Now tell me, for a reaction to be feasible thermodynamically, delta G has to be less than zero. Entropy, free energy change has to be less than zero. Now we notice that this is positive, this is positive. The only way I can make delta G negative is if temperature increases, then only delta G will start becoming negative, or delta G will be negative, isn't it? Everyone clear with this point? And this is where you need to understand, everybody, that as the temperature increases, free energy change decreases. That means the reaction will go more in the forward direction. And that's the reason why heat is essential in all elimination reactions. And what did we learn out of this case is every elimination reactions are endothermic. Energy is required for them. That's why higher temperature will always help it go towards elimination more than substitution or any other reaction type. I hope the basis of the elimination and even is clear. And even is one of the kinds where instead of reaction directly forming the products, first it is giving carbocation. Do you remember the Hammond's principle now? Let us try to recall that. See, from the reactant Rx, on its own it has went all the way to become a intermediate, which is carbocation. And from the carbocation, it is going all the way to become a product, which is alkene in this case. Yeah. In this, have you noticed the first step is the rate determining step, obviously, because it has a high activation energy. And the intermediate transition states stability depends upon carbocation stability. If a carbocation is more stable, transition state energy will be less, activation energy will be less, and reaction will happen faster. Which means the rate of reaction depends on stability of carbocation. Now you can notice that why I have written this. Rate of reaction depends upon stability of carbocation. Very important term. Clear? Okay. Rate of the reaction depends upon stability of carbocation. And see, according to rate law, because we haven't done kinetics, I'm just giving a basic suggestion here to understand something called rate law. Okay. Rate law is a theoretical way of expressing the rate. Okay. In this case, what is happening? We have a reactant. This is the overall reaction, correct? Okay. So in the overall reaction, have you noticed the first step is the rate determining step, and rate law is always written for the rate determining step. So first it is becoming a carbocation. It is becoming Cl minus. Okay. This is the rate determining step. Therefore, rate will be equal to some constant into concentration of alkyl halide raised to power of 1. So if the stoichiometry is 1, you will write here as 1. Okay. And that one which you have written is called as the order of the reaction. Order. As of now, you just remember this term. Order of the reaction. So what is the order of the reaction? Order of the reaction is 1. Okay. Now, have you noticed something? In the rate determining step, how many molecules are involved to convert into a product side? The product side is carbocation and Cl minus. So for this alkyl halide to convert into this carbocation and Cl minus, you require only one alkyl halide. If in the rate determining step, there is only one reactant being used, you call it as a unimolecular reaction. The type is called unimolecular reaction. So you can see it is unimolecular reaction. So basically, everybody, we are studying about an elimination type where there is one molecule involved. That's why it is called E1 reaction. That one represents not the order, everybody, it represents how many molecules are involved in the rate determining step. Clear? So we are learning about elimination type 1. 1 means unimolecular. Okay. Now, obviously, which alkyl halides can give more stable carbocation? The stability of carbocations we have already learned, everybody. 3-degree carbocation will definitely make more stable compared to that of 2-degree, compared to that of 1-degree, compared to that of methyl carbocation. Hence, the rate of reaction for 3-degree alkyl halide, 2-degree alkyl halide, 1-degree and methyl alkyl halide goes in this direction. This is the order of the rate. Please let me know if you have understood this or no. If there is any problem in that, I'll explain it again. Please go through it once quickly. Everybody, check this out carefully one by one. Reactivity, we just learned that reactivity of E1 type. So I can say tertiary will be greater than secondary, greater than tertiary, primary, than methyl. Next one is elemental effect. That means the rate also depends upon which type of halide that is connected. You know that carbon iodide bond is weaker compared to carbon bromine, carbon chlorine, and carbon fluorine. So it's much easier to relieve the iodine bond, break iodine bond compared to fluorine. That's why, since the bond dissociation energy is in this particular order, the reactivity will be in this particular order. The reactivity will be in this particular order. Just yesterday's question. Okay, yesterday's session, there had been a question on reactivity. Got it? So check out. This is called elemental effect. That means an element is affecting the rate. The iodine's presence, bromine presence, chlorine presence, and fluorine presence will change the rate of the reaction. Got it? Next, let us understand what is regioselectivity of E1. For instance, if you have this type of alkyl halide and I'm treating that with ethanol, okay? Step by step, if you go for E1 mechanism, what is that you will get? See, first you will get a carbocation here. That is the first step. And rearrangement is expected to happen, but unfortunately, this is already in the most stable position. So no rearrangement here. Then the position where the carbocation is present, that is called alpha, and the adjacent carbons are called as beta. Adjacent carbons are called as beta. Now, have you noticed that the ethanol have a choice now? The choice is it can go extract a proton from this beta position, or it can go and extract a proton from this beta position. Correct? It can expect, I mean, we can expect this to get proton from either of these two positions. Yes. In such case, what would happen? See, in that case, there are two types of alkenes that can form. One is a double bond here. You might say, sir, what about this beta? Have you noticed this beta and this beta is same only? It's no different. Removing H plus from here or H plus from here is same, because you'll get the same type of alkene. So this is one type of alkene I can get. The other type of alkene is like this. Count the number of alpha hydrogens. Recall hyperconjugation, everybody. So here there are 3, here there are 2. So total how many? 5. Count the alpha hydrogen here. Here we have 3, 3, 3, 9. So which one is more stable? If I write this as product 1 and product 2, I can say stability wise, product 2 is more stable than product 1. Correct? Now imagine the mechanism from here, everybody. Suppose if I already have reactant reaching towards one intermediate. From the intermediate, it has two particular directions. One going towards product P1, P1. The other one going towards a product P2, like this. Going towards product P2. Okay? Because P2 is more stable, its energy will be less. And notice this one. Here, the activation energy required here in this particular case is E1, and activation energy required here, this is E2. And you can clearly notice that activation EA1, again, it will confuse with that elimination type, EA1 and EA2. So elimination EA1 and EA2, if you compare, EA2 has more amount of energy. That means it will be slow process. Secondly, it is not giving stable product. It is giving less stable product. But P2 is a more stable product and activation energy is less. So which is more preferable? This one is more preferable. So the elimination route will be such that you will get this as a major product and this as a minor product. This as a minor product. Got it? Correct. Now have you noticed something? These two are isomers of each other. Correct? These two are isomers of each other. And most importantly, out of these two isomers, notice one thing. Correct? You are getting something like a positional isomers here. So you can see the double bond here and double bond here. So that means position is nothing but a region. Have you noticed that ethanol had two regions to choose? From here, it could have chosen this beta hydrogen or it can chosen this beta hydrogen. It chose one over the other. That means, of course, this is also happening, but in a very small amount. Here, this elimination is happening in a large amount. Correct? So that means it is choosing one particular position or particular region from where hydrogen can be drawn. So such type of mechanism where a region is very specific to choose, we call it as regio specific mechanism, which means I can say E1 is a regio specific mechanism. And a regio specific mechanism will always give us a product which is more selective, and that's what it is called regio selective product is formed. So P2 is a regio selective product. That means out of the two mechanisms, one mechanism was heavily chosen, or I would say it will driving towards major product, and major product has become P2. So product is called as selective product. The mechanism is called as specific mechanism. Clear with these two terms, everybody? The next important term. See, out of these two, out of these two products, out of these two products, over a double bond, I have one and two substitutions. One methyl, one ethyl. Agreed? Everybody? Across double bond, I have two substituted groups. But across this double bond, I have one, two, and three substitutions. If the substitutions are more in a product, that product is called Shezef or Zezau. This is a Russian word. This is the Indianized word. Okay. So it is Shezef. You call it as Shezef or Zezau. So the product which is having more amount of substitutions on a double bond is called as Shezef, and the product which is having less number of substitutions, that is called as Hoffman product. That is called as Hoffman product. Clear, everybody? The regioselectivity of E1 is clear. That why it is choosing a particular region over the other, because it is deriving more stable product. Activation energy is less, transition energy is less on this direction. That's why it is choosing that. Right? Since one product is coming as major, it is called regioselective product. So you can notice this example. In this example also, chlorine is here. When you react with ethanol and heat, there is one beta here and one beta here. If ethanol takes H plus from here, you will get this particular product. If it takes H plus from here, you will get this particular product. This has two substitutions, this has one substitution. So this is Hoffman product, this is Shezef product. Usually people, if you are going through even mechanism, Shezef product is major product always. Okay. Now, within the Shezef product, have you noticed something? Within the Shezef product, I could have got cis or trans, correct? I could have got cis or I could have got trans. That means the product could have been like this or the product could have been like this, correct? Within the major product, everybody, if you are getting, if you, the chances of getting cis and trans, both of them are present, tell me which one is more stable. If you check out the stability wise, if you check out the stability wise, you know that generally trans alkenes are more stable than cis. Very exceptional cases might be there, but otherwise trans is more stable than cis. Hence, since trans is more stable than cis, the chances are within that major product, again it will choose to be one of them being major. It is like this. Suppose I got this as 3 percentage and this as 97 percentage. Now I'm saying within that 97 percentage, probably 60 percentage is this one and maybe 37 percentage is this one. This is what I'm trying to tell you. Clear? So it will not be like 50-50 percentage. So if I ask you with the isomerism also, with the stereoisomerism, that between cis trans, which is major, generally for even mechanism, you'll always choose trans as major. Chances of getting trans is much more likely compared to that of cis. Clear? So you notice that stereochemistry of even, how is it? Check it out. I'm trying to explain the stereochemistry part, everybody. Look into it carefully. You know that when you have first even mechanism, we expect it to go via carbocation formation. So what do you mean by carbocation? That means it is a carbon having an empty orbital across a plane like this, correct? Across a plane like this. In this plane, one is methyl, one is ethyl, the other one is hydrogen, correct? Because this carbon holds one hydrogen, one methyl, one ethyl. And this entire system, hydrogen, methyl, and ethyl, are on one particular plane. They're on one particular plane here, correct? And then I told you that this methyl, I mean, this ethyl can be now written as CH2, sorry, with one hydrogen bonded here like this. Got it? And of course, if the bond is there on that side, this will be sigma star orbital. All right. And then we have CH3 on it like this. All right. Now, what would happen when the base like ETOH, ethanol, is coming and taking away this hydrogen? The electrons which are left over will start pushing them to make pi bond here, because this is an empty orbital, completely empty orbital. So that's how that sigma star will slowly convert into pi and pi bond is forming. Okay. Now, when this pi bond is forming, it will look into support of the adjacent groups. Now you can see methyl can support. This methyl can support both by plus psi effect as well as by hyperconjugation. And because you are getting a good amount of support in the trans case, that's why it will prefer trans over cis. So trans will have more support of plus psi and hyperconjugation being more than plus psi and hyperconjugation of cis form. That's the reason why the stereochemistry of E1 chooses to go for more trans rather than cis. Okay. So even mechanism, everybody, please remember that what happens to the stereochemistry part of it. Okay. Next. If you compare the rearrangement of carbocation, got it? This is another important part, that whenever you have a carbocation forming, immediately does it form product? No. It will give multiple products, but it will give the most stable product based upon the most stable carbocation formation first. So stability of the final carbocation will decide the major product. Let me show you how with an example here. See, for instance, here, if you have chlorine here, so first we'll get a carbocation here by removing the chlorine. So let me say the chlorine minus has gone. And once you get this carbocation, it will give a methyl shift. You know that this methyl can shift here, making into a methyl shift. So we will get a carbocation like this, correct? And from here, it cannot go any further. It cannot go any further. So now when the ethyl comes into the picture, ethyl realizes that this is alpha, beta, and beta. With respect to that, here on this beta, there is no hydrogen. It can't do anything. But the product, what it lays down is like this. Only this side you will get one product. This is the minor product, but yes, you will get this product. Similarly, here when you have, there are two types of beta. You have a beta here and you have a beta here. Of course, this beta and this beta are same. Now, if the elimination happens, there are two types of products I can get. One product is double bond here like this, and the other product is double bond here like this. Okay. Now count the number of alpha hydrogens, everybody. Here it is 0. Here we have 4. Here we have 12. So which one is major? This one is major product. Okay. And of course, these two are minor. Within the minor, this is a better minor. This is the least minor, which is in traces. But listen, if the question is coming in JE, and if the question is asked, what are the maximum number of products? Then you have to mention all three. Maximum number of products which you can get is all three of them. Clear? See the next one. Suppose if we have ethanol here, removing this chlorine, see, usually I told you that we need to get a stable carbocation. Unfortunately, here the carbocation is not very stable. Okay. You have a plus charge here. It is not very stable. It is in a primary position. There is only plus psi effect. But Still, this will go for E1 because the next step makes it very, very stable form. So you can see from here, the methyl shift can happen. How do we read it, everybody? We call it as 1,2 methyl shift. It is called 1,2 methyl shift. So as it happens, so you will get a carbocation here first. Correct? So from this carbocation, right, you can start fetching towards the products. So how many products I can get from here? Also, you can get a product. We'll see whether there is a product formation. Here you can get two products. I'm directly writing the products, everybody. You can see one double bond here and one double bond here like this. Can you get a product from here? Answer is no, actually, because for this positive charge, this is only beta, and on that beta, there is no alpha hydrogen. So how many maximum products? So maximum number of products formed in this case is only two. You cannot get more than that. Clear, everyone? Notice the next question. Suppose if you have this ethanol here and you're heating, the first thing what you will do is make a carbocation. This one. Unfortunately, this carbocation is already at a very stable position. So because it is at a stable position, now you can notice that this is alpha, beta, beta, and beta. Since it is already at a stable position, there are two products I can expect. One is like this. The other one is like this. These two are the products expected. And you can clearly make out the alpha hydrogens here are 7, alpha hydrogens here are 4. So which is major? This one is major and this one is minor. And maximum number of products you can get. Maximum number of products you can get here are only 2. Okay. So see the next case. The next case goes something like this. Here first I need to make a carbocation like this, and then it can be further converted into more stable carbocation by 1,2 methyl shift. That means this methyl can be pushed here, thus making it to a more thus making this into a more stable carbocation where methyl shifts here, one methyl will be left and positive charge will be present here. Okay. Now check out very important case. This one is, if the question is asked, what are the maximum number of products? See, check out carefully. From here, if you notice, there is beta here, beta here. This side of the beta does not have any alpha hydrogen. Therefore, the product what you will get, everybody, will be like this. Double bond here and this particular group. That's it. This is one compound we can get. Clear? Right. Second one, on this side, if you come across here, see the products. One, with respect to this, alpha here, beta here, and beta here. All three betas are different. Sorry. All three beta cases are different, everybody. So what are all the products you can get? The first one will be with a double bond here like this. Second one will be with a double bond here like this. And third one will be with a double bond here like this. This is the case we have. Okay. Now listen up. As per JEE mains also, if the question is asked maximum number of products form, you have to count the stereoisomers also, everybody. Now check it out. This is one, this is one, but here there is a chiral center, makes it as two. Again, there is a chiral center, makes it as two. So what is the answer now? 6. So total number of products formed are 6. A very, very similar type of question was asked, in today's session. Okay. I mean, I can tell you the question number also. I can just, I don't want to show it because you have to do it in the later stages. But a very similar type has been asked. Correct? Bromine was given instead of chlorine, and then he asked how many maximum number of products he got. Answer was six only. Got it? Clear. Next, check out in this case here. Okay. Now, in this case, you can clearly make out. First, you have to make a carbocation here. So we get phenyl, ethyl, methyl with carbocation. And next, you have a chance to shift phenyl, ethyl, and methyl. Typically, we make a phenyl shift. We will usually make a phenyl shift. Okay. So if you make a phenyl shift, because usually in such cases now, you will be definitely given the migrating aptitude, that which one should be shifted. That will be mentioned to you, whether we should shift phenyl or ethyl or methyl. By chance, if it is not given, then follow the order. Migrating aptitude order. Migrating aptitude order is hydrogen, then phenyl with electron donating groups, phenyl which has electron donating groups on it, or only phenyl, or phenyl with electron withdrawing groups. And then comes 3 degree, 2 degree, 1 degree, ethyl and methyl. So methyl is the worst one. So phenyl, if you shift it, what do we get here? So notice we will get ethyl, methyl, then phenyl here. And next I'm getting a positive charge here. So it is ethyl and methyl. Got it? Now, actually, this is not even a more stable state. In fact, the hydrogen will shift from here again so that you can get a stable state like this. So phenyl with carbocation here. So 1,2 hydrate shift. So this is the most stable form which you have. Considering phenyl shift, everybody. You might be able to debate it, sir. Why not we directly shift ethyl instead of methyl? That will be given in the question. Don't worry about it. But if the question is said, phenyl go shift karo, you do this and proceed afterwards. Now you decided the stable carbocations in this case. Now go for elimination kind. So from here, as you go towards the elimination, what do I get? Because left side there is no beta hydrogen, you will get only double bond here. We will have phenyl, ethyl, and methyl. Done. Next, if you compare on this one, you will have double bond here. This is one double bond, everybody. Methyl and ethyl. And then notice here also when you write ethyl, basically what is ethyl? Ethyl is nothing but CH2CH3. So beta कितने type के हो गए? Beta, beta, beta. There are three different types of beta. So I'll get that product also. So I need to write this particular product with double bond here and methyl. On this side I'll write methyl, methyl here and phenyl here like this. Okay. And one more product which I have. Let me write down. I'll shift a bit here. Yeah. One more product which I can have here is this one, where I can have like this with phenyl and double bond here on this side. So structurally, these are the products I can get. I have not counted stereo yet. Okay, so let me finish the rest of the part, then we will count it. So here it is ethyl and methyl. So one is I can get a double bond here. I can get a double bond here like this with phenyl, ethyl and methyl. And the other case which I can get here is double bond over this side, phenyl, ethyl and methyl. Done. These are all the possible cases which I have written. Now notice one by one. First case, there is still a chiral center, makes it at two products. Now there is no chiral center, but there is cis and trans. So that makes it 2 again. Cis and trans can come. Yes, everybody. Next, here also there is cis and trans and a chiral center. You can see here I can get cis and trans and I also get a chiral center. So that means how many should I count as a product? 4. Here I can't have cis and trans, but I have a chiral center. That means I'll count it as 2. Next. Now, have you noticed that this product and this product is same? Because this is same, I'll just write it as same or duplicate. I don't have to count it. Okay. Next, here again there is a chiral center which makes it 2. Check. 2, 4, 8, 10 plus 2, 12. So total 12 products. Total 12 stereo isomers. I mean, total stereo isomers here. Or total 12 products. Maximum number of products that is asked is 12 products. Any doubt here?
So,
Yes, beta.
so in the third figure where you have marked 2 stars, why are there 4 carbons? Because from what I can see, there is 1 chiral center and cis and trans. So there should be 3.
Okay. See, here, this ethyl, I made it into a double bond here, no, beta?
Yes, sir.
So there is one methyl here, and one methyl here.
Hmm.
Correct? So that's
Yes,
why
sir.
methyl, and methyl. Got it?
Yes, sir.
And because you have these two methyls, they can be on the cis side or they can be on the trans side.
Yes, sir. Understood.
Correct? Hmm. So I want all of you to notice that carefully. Any doubt? Right. To summarize the even mechanism, now notice all the terms here. Reactivity of alkyl halides. Okay. Generally, it is 3-degree alkyl halide. Okay. 3-degree Rx greater than 2-degree Rx greater than 1-degree Rx greater than CH3CH2X. Next, stability of alkenes. Correct. So you should check out based on alpha hydrogen. So this alkene is more stable than this alkene, more stable than trans alkene, is more stable than cis alkene. This is the order in which you need to check. Weak base solvents. Okay. See, the solvent itself will act like a weak base. That's why weak bases includes water, alcohol, acids. Got it? Sometimes I minus. Okay, I minus salt. Got it? And that's it. These are the ones which we typically use it. Okay. Ammonia, rare cases. Rare cases, it will go for E1. Otherwise, ammonia is a relatively stronger base, so it will go for E2. And polarity of the solvent should be high. Higher the polarity, more is the E2, E1 favorable. So if you compare the E1 rate, okay, in water, it will do better than alcohol. Agreed? In water, the polarity is more. So it will do better elimination in water than alcohols. Bond dissociation energy of leaving groups, I told you that Ri will be lesser than RBr will be lesser than RCl will be lesser than RF. Stability of carbocation, we learned that 3-degree carbocation is more than 2-degree carbocation, more than 1-degree carbocation, more than methyl carbocation. So that's the order we need to follow. Temperature, as temperature increases, E1 mechanism is more favorable. So I hope everybody understood the crux of E1 mechanism. All right. These are the important points that you need to learn from E1 mechanism, everyone. Okay. I have given some questions here. You can go through it. First, you complete this part, and then next class we can discuss on E2 mechanism.